Hi there, this is exercise 1b. We're looking today at more proof by mathematical induction. Up to now we've looked at examples from mainly the Year 12 book, which were like differentiation, sequence, some kind of sequences, iterative sequences. Sometimes proof by divisibility, prove something as a multiple of 4, something like that. Matrices was another one I remember. Inequalities was one. The one we haven't touched on yet is series, and series is possibly the most important, so we're going to look at it now. So just a brief reminder, there's a 4-step process. We check for n equals 1, we assume for n equals k, we prove, and this is the tricky bit, we prove the inductive step for n equals k plus 1, and then we write out the completion statement, which is given there. You obviously need to learn that. I've spoken to you about that before. So here's my first example, and if we just look at it, it says prove for r equals 1 to n that the sum effectively of r squareds is this formula. And we just crack on. So step 1 then is we check for n equals 1. And when n is 1, the left hand side, i.e. this bit, is the sum of all the terms up to 1 squared, which is just 1 squared, which is 1. And the right hand side, basically I put n equal to 1 into this, and I get a sixth of 1 times 2 times, well this is 2 times 1 is 2 plus 1 is 3. That makes 6. A sixth of 6 is 1, so therefore it's true for n equals 1. So far so good. And number 2, well we assume, and this is just the writing bit, it's not hard at all. Assume for n equals k. Up to now it's very similar to what you've seen before, so we basically just rewrite the sum from r equals 1 to k of the r squareds is a sixth k plus 1. 2k plus 1. And the inductive step, the tricky bit, this is where I prove for n equals k plus 1. And the key here is to realize, and this is the trick we're going to use on all these series, that if I want the sum from r equals 1 to k plus 1, then essentially it is the sum of from r equals 1 to k plus an extra term. And it's the k plus 1th term, where k plus 1 goes into this left hand side. So this is about r squared, so it's plus that. And of course the great thing is we know, well we've assumed that this from 1 equals 1 to k is a sixth of k plus 1, 2k plus 1, keep on getting that a bit wrong, plus my extra term, my k plus 1th term, which is k plus 1 squared. And so I'm going to take out as a common factor a sixth, because it's the lowest common denominator, that hasn't got a fraction. And then it's just of k plus 1. And I see what I times the first thing by. I would times, well, I get a k and a 2k plus 1. Plus, what's this? Well, I need to deal with the 6. There isn't a 6 there, so it's 6 lots of, and I think this is k plus 1. So what's that give me? It gives me a sixth of k plus 1, and now I'm going to multiply out this square bracket. It's 2k squared plus a k, don't forget your 6k, don't forget your 6. And this is a sixth of k plus 1. Now, you can kind of cheat a bit. You can kind of know that, obviously I've got really 7k here, so I'm going to hazard a guess. This is 2k plus 3 and k plus 2. That gives me 2k squared plus 4k plus 3. Yes, that works. And the reason I did that was because I substituted k plus 1 into here, which gave me k plus 2, which is this one, and I put k plus 1 into here, which gave me 2k plus 2 plus another one, which is 2k plus 3. Now you probably would just type into your calculator and factorise it, but I did it properly. With a bit of a cheat. And obviously then I'd need step 4, and it's the wordy bit that you write out after each time. I'm not going to do it now. So here's another one. Prove by induction that this is true. Now what have we got? It's the sum of all this. So we're going to check first n equals 1. And when I put that into the left-hand side, what I get, the first term is 1 times by 2. No, not 2, it's 1 times by 3, because 1 plus 2. And that equals 3. And the right-hand side, of course, is the formula. And that's 1 times by 1 plus 1 is 2 times by 2 plus 7 is 9 divided by 6, and that's 18 divided by 6, which is 3. So yeah, it worked again. Well, I'm not surprised, we expected it to. Now we assume, I'm going to write the word assume, that the sum from r equals 1 to k of r plus 2 equals this k plus 1, 2k plus 7 over 6. Okay, there's our assumption. R3, this is our proof. I'll write it, n equals k plus 1. So for n equals k plus 1, again we're using the idea that the sum from 1 to k plus 1 equals the sum from 1 to k plus the extra term, and the extra term comes from this bit. So the left hand side there gives me k plus 1, remember that is my r, and then I've got to add 2 to it, which will give me k plus 3. That's the trick you've got to suss. Let's work it up here. So this then gives me, well, I know the first assumption was k plus 1, 2k plus 7, a sixth of all that, plus k plus 1, k plus 3. And you can see it's very similar to the last time, as much as I'm going to take a sixth out and k plus 1 out. They appear in both. Well, the sixth doesn't, but we've seen that trick before. So here I get a k and a 2k plus 7. And what do I get here? I get a k plus 3. It's very similar to this. It's not much different. It's a sixth of k plus 1. Multiply out the bracket, I get 2k squared again, plus 7k, plus an extra k there, that's 8k, plus 3. And again, I think this becomes k plus 1, obviously, because we've got that now. And I think I'm going to get, when I do this, 2k plus 9. Or is that right? I'm not convinced now. K plus 2. I've done something wrong here. Just pause. Well, I've sussed my mistake anyway. It's here. So my mistake was I took out a sixth, and I didn't reflect that here. So effectively I've got to times these both by 6. So that gives me 6k plus 18. Which gives me, when I do this, then I get 7k and 6k, it gives me 13k plus 18. And now I reckon that works. 9 2s are 18, which that gives me 9k plus 4k. Yeah, that works. And obviously that is the given result, etc. So you write all that out, and then we're done on that. So first two are done, allowing for my dodgy mistake on the not taking the 6 out as or including it. My third example then. Now this is not written in quite the same way. I suppose I just need to get my head around this, what they've got here. This is the sum of all the terms from r equals 1 to n of this thing here. That's what it's meant to be. So of r, notice I've had to change it to the r. And that n term tells me really what my term is here. Anyway, I'm going to prove it. So for n equals 1, the left hand side of this thing is just simply 1 times 2, which is 2. And the right hand side is the formula over here, which is a third of 1 times 2 times 3, which again is 6, divided by 3 is 2. So tick does work for n equals 1. So first part done. Second part, we check for n equal, we assume for n equal k. So therefore I'm assuming that this r equals 1 to k of r plus 1 is equal to a third of k, there you wrote n then, k plus 1 and k plus 2. So assumption out of the way, we now do our tricky step. Now hopefully you're sussing they're all the same really. So here we are saying the sum from r equals 1 to k plus 1 is again the sum from r equals 1 to k plus our extra term. And our extra term will be this extra term, this left hand side if you like, and it will be k plus 1 times by k plus 2 when I substitute the k plus 1 in for the n. And what's that equal? Well, the first bit is a third k plus 1, k plus 2. I'll try not to make a mistake this time, plus this k plus 1, k plus 2. But in essence, it's very similar. So I'm going to take out a third of k plus 1 again. Oh, I can also take out the k plus 2, just realised. Is that, no, that's where I've gone wrong here. This is k plus 1. No, that's right. No, that's right. That's not right. No, that's right. Yeah, bear with me. I'm just trying to get my head around what I've done. No, that is right. So I can take out both of these things. And that gives me a third of k. That's the k that's missing on that. And this is perfect other than it's got a third. So therefore it's 3. And that is actually the right answer. Because that's with k plus 1 replacing the k. So again, you'd have to write out step 4. But other than that, we're good. Ooh, that's it. We're done. There was only the 3 examples, I think. So more or less, now there are harder versions. Now the harder versions I would suggest come about, and I build on this in the revision exercise later on. But you can get examples that go from 1 to 2n. So look out for examples like that where you get some expression. And just remember that you just substitute 2n there. And so you can also get ones that go from, say, n up to 2n and stuff. So if you're doing that, you're basically saying that's the sum from r equals 1 to 2n of whatever term it is, minus, now I start here at n. So if you imagine the number line here going 1, 2, 3, all the way up to n. And of course the one before it and after it, well, that's n plus 1, and then n minus 1 before it. And then it carries on going, and eventually it would get up to 2n. Now in my example here, which I've just made up admittedly, I want from n to 2n, so I want all of those. So to get those, I go from 1 to 2n, all of them, minus this little lot. For that reason, it starts at r equals 1 up to n minus 1. And that will get me that. So I work out this one, I'll work out that one, and try and solve the answer. Now, I'm not sure what your exercise will have, but I bet I wouldn't be surprised if some of the later ones are like that. So just have a look at that, see what you can do, and see if that's okay. But bear in mind, I come back to this in the revision exercise later on. So you can have a go at that as well. All the best.